Today we are going to solve two problems on Pelton wheel, Pelton turbine. So, the first problem, let me read it out. A Pelton wheel operates with a jet of 150 millimeter diameter under the head of 500 meter. Its mean runner diameter is 2.25 meter and it rotates with a speed of 375 rpm. The angle of the bucket tip at the outlet is 15 degree. The coefficient of velocity is 0.98. The mechanical losses equal to 3% of power supplied, and the reduction in relative velocity of water while passing through the bucket is 15%. So we have to find the force of the jet on the bucket, the power developed, the bucket efficiency, and the overall efficiency. So as you can see, this is the bucket of the Pelton wheel. This is the peripheral velocity of the bucket. This is the absolute velocity of water at the inlet, or the jet velocity. This is the angle by which the jet gets deflected after it hits the bucket, and this angle is beta 2. So let me write the parameters that we are given. Firstly, we are given the jet diameter, which is 150 millimeter or 0.15 meter. The head at the inlet is given as 500 meter. The mean runner diameter is given as 2.25 meter. The rotational speed of the runner is given as 375 rpm. The angle beta 2, that is this angle, is given as 15 degree. The coefficient of velocity is given as 0.98. Now, this line actually signifies tells us the mechanical efficiency. So from this line we can actually say that the mechanical efficiency is given as 1 minus 3%, that is 0.03, that is 0.97. So this is the mechanical efficiency. Also we are given that the relative velocity of the outlet has a reduction of 50% compared to that of the relative velocity at inlet. So we can write VR2, that is the relative velocity at outlet, is equal to 0.85 into VR1. So these are what we are given. So first we are going to find out what is the force of the jet on the bucket. That is F. Now we know that the force is given by the expression rho q into the tangential velocity at the inlet minus the tangential velocity at the outlet. Q is the flow rate of the jet. So we know already the rho, which is the density of water, and that is 1000 kg per meter cube. So we have to find out the flow rate of the water at the inlet and also the tangential velocity components at the inlet and the outlet. So for the flow rate, we know it is given by into the jet velocity, where d is the diameter of the jet. We know this. We have been given this value. So we have to find out the jet velocity, which is given by V is equal to the coefficient of velocity into root over of 2 into g into the available head. Now we know all these quantities. All these quantities have been given. So if we substitute the values, the jet velocity comes out to be 97.06 meter per second. So substituting the value of V into the above expression, we find out the value of Q, which comes out as 1.714 meter cube per second. Next, we have to find out the tangential velocity at the inlet and the outlet. For this, we refer to the velocity diagram for the Pelton turbine. So, here first we see the inlet velocity diagram. Here, this is the peripheral velocity of the blade, this is the relative velocity at the inlet, and this is the tangential velocity, which is also equal to the absolute velocity of water at the inlet. So, from here we can write, we know that the tangential velocity of at the inlet is nothing but the jet velocity. So, we know already, we have already found out the jet velocity, and which is 97.06. So, let us move on to the outlet velocity diagram. In the outlet velocity diagram, this is the tangential velocity at the outlet, this is the relative velocity at the outlet, and this is the absolute velocity of water at the outlet, and this is the peripheral velocity of the blade or the wheel. So, here we can write the tangential velocity as, from the velocity diagram we can clearly see that it is equal to u minus V r 2 cos of beta 2. Now, beta 2 is given, V r 2, as was already said in the problem, is equal to 0.85 into V r 1. Now, from the inlet velocity diagram, we can see that V r 1 is V 1 minus u. So, substituting, so okay, you have to, so we have not found out u also. So, we have to find out u, that is the peripheral velocity of the blade. So, the peripheral velocity of the blade is given by pi into the runner diameter into the speed of rotational speed of the runner divided by 60, since n is in rpm. So, we know the runner diameter and also the value of n, which is 375 rpm. So, substituting the values, we get the value of u as 44.16 meter per second. So, from this expression we get the value of V r 2, that is the relative velocity at the outlet, as 44.965 meter per second. So, after all, so finally we have found out the relative velocity at the outlet. So, returning to this formula, to this expression, we find out the velocity of V w 2. We know u, we know V r 2, and this has been already given. So, the velocity for the tangential velocity at the so the value of the tangential velocity at the outlet is 0.73 meter per second. So, finally, the force whose expression was given as so, substituting all the values here, we finally get the value of the force on the bucket by the jet as 165.15 kilonewton. So, moving on to the next part, where we have to find out the power developed. This is given by the above force multiplied by the peripheral velocity of the blade, which is peripheral velocity of the blade was found out earlier and as 44.16 meter per second, and which this comes out as 7.3 megawatt. Next, we have to find out the blade efficiency. The blade efficiency is the ratio of the power input to the output kinetic energy into 100. So, the output so the input sorry, I made a mistake. The blade efficiency is the ratio of the output power divided by the kinetic energy, input kinetic energy of the jet. The output power is we just found out earlier as 7.3 megawatt, and the input kinetic energy is basically given as the kinetic energy of the jet, which is rho q v1 square, rho q dot v1 square by 2. So, we know the value of q dot, we know the density, and we have found out v1 earlier. So, substituting the values, we find it to be 90.4%. So, finally, we have to find out the overall efficiency, which is the product of the blade efficiency and the mechanical efficiency. As we have, while I was writing out the data, we found out that the mechanical efficiency was 0.97. So, from here, substituting the values of the respective parameters, we find out the overall efficiency as 87.7%. So, this is the end of problem 1. Now, I will be moving on to the problem 2. So, let me read it out. In a hydroelectric scheme, a number of Pelton wheels are used under the following conditions. The total output power required is 30 megawatt, a gross head of 245 meter, and the rotational speed of the runner is 6.25 revolutions per second. Per wheel, there are 2 jets used. The coefficient of velocity is 0.97. The maximum overall efficiency is 81.5%. The dimensionless specific speed, or the maximum value of the dimensionless specific speed, is given as 0.022 revolutions per jet. The head lost due to friction in the pipeline is 12 meters. The ratio of the blade to the jet speed is 0.46. So, we have to find out the number of wheels that are required, the diameters of the jets and the wheels, the hydraulic efficiency. Also, we are given that the deflection angle of the water jet after hitting the blade is 165 degree, and again, as the previous problem, the relative velocity at the outlet is 15% is reduced by 15% compared to the relative velocity at the inlet. So, also we have to find out the percentage of input power which remains as kinetic energy at discharge. So, let us write down what are given in this problem. So, first we are given with the output power that is required, which is 30 megawatt. The gross head is given as 245 meters. The rotational speed of the runner is given as 6.25 revolutions per second. Number of jets used per wheel is 2. Coefficient of velocity is given as 0.97. The overall efficiency is given as 0.815. The dimensionless specific speed of the turbine is given as 0.022 per jet, and the head loss due to friction is given as 12 meters. Also, the angle beta 2 is given as 15 degree, just like in the previous problem. So, first let us try to find out the number of wheels that are required. For this, we need to find out the output power required per wheel. So, first let us write down the expression for the specific speed for turbine. It is given as the rotational n into p to the power half divided by rho to the power half into gh whole to the power 5/4. So, from here we know the value of the specific speed, the maximum specific speed, which is given. The rotational speed of the runner is also given. We know the value of the density of water, we know the value of g and h. This h is the net head available at inlet, which is actually the gross head minus the frictional head loss, that is 233 meter. So, from this we can find out the power required per wheel for each jet, and if we put the values, it comes out to be 3.09 megawatt. So, the number of wheels is the total power output divided by the power per wheel per jet into 2, since two jets are required per wheel. So, this comes out approximately as 5, which is the nearest whole number, and we have to take the whole number for this case, since we have to find out the number of wheels. So, moving on to the next part, where we have to find out the diameter of the jets and the wheels. So, to find out the diameter of the jet, we can write that the flow rate of water of the jet is pi/4 d square into the jet velocity. Now, this is also unknown, and as well as the velocity of the jet is also unknown. So, let us first find out the velocity of jet, which is given as Cv into root over of 2 into g into the net head available. We know all the values, and so substituting them, we find out the value of the jet velocity as 65.58 meter per second. Also, the flow rate we have to find out. So, for this we write an expression for the power output per wheel per jet as g h rho q dot into the overall efficiency. So, we know the net head available, the density of water, and we know the value of the power per jet we have found out earlier. So, from we know the overall efficiency also. So, from here we can find out the flow rate per jet for one jet as 1.66 meter cube per second. So, right now we know what is the value of q dot and as well as the velocity of the jet. So, we can find out the diameter of the jet as by substituting the values, which comes out as 179 millimeter or 0.179 meter. Next, we have to find out the diameter or the mean diameter of the runner. So, we know that the peripheral velocity of the blade can be expressed as pi d n, where n is in revolutions per second. So, here we have to find out the peripheral velocity of the blade. Now, in the problem, it was given that the ratio of the blade to jet speed is 0.46, that is u by v 1 was given as 0.46. So, from this we can find out the velocity peripheral velocity of the blade as 30.17 meter per second. So, substituting this value of u in this expression, we know the value of n. So, we get the runner diameter as 1.54 meter. Next, we have to find out the hydraulic efficiency. The hydraulic efficiency is given as the tangential velocity at the inlet minus the tangential velocity at the outlet multiplied by the blade peripheral velocity divided by g into net available head into 100. So, let us move on to the velocity diagrams to find out these quantities. Here V w 1, as earlier we have said, V w 1, that is the tangential velocity of the inlet, is equal to V 1, the jet velocity. So, V r 1 is equal to V 1 minus u or u 1. So, substituting the values of V 1 and u, we already know, we find out the value of relative velocity at the inlet, which comes out as 35.41 meter per second. Next, from this triangle, from this velocity diagram, we have to find out the tangential velocity at the outlet, which is given as V w 2 is equal to u minus V r 2 cos beta 2. V r 2, as we already know, is given as 0.85 into V r 1. So, substituting the value of V r 1, we ultimately get the radial velocity at outlet as 30.1 meter per second. From this, we know the value of u, we know beta 2 is equal to 15 degree centigrade, 15 degree, sorry, and we get the value of tangential velocity at outlet as 1.1 meter per second. So, right now we have known the values of V w 1 and V w 2. We know the value of the peripheral velocity of the blade, we know the net head available. So, we can find out the hydraulic efficiency by substituting the value, which is 65.58 minus 1.1 divided by 9.81 into 233 into the peripheral velocity of the blade, which is 30.17 into 100. Calculating this, we ultimately get the hydraulic efficiency as 85.1%. Finally, we have to find out the percentage of the input power which remains as kinetic energy of water at discharge. That is, we have to find out the ratio of the kinetic energy at output with respect to the input power. We find out this ratio for both the quantities per unit mass. So, the kinetic energy output per unit mass is given by V2 square by 2. Now, from the velocity diagram, we have to find out V2. Now, as you can see, V2 is given as, or V2 square is given as VW2 square from this triangle, VW2 square plus VR2 sin beta 2 square. We know the tangential velocity at the outlet or VR2, we know beta 2, and we also know that we also know the value of VR2 and beta 2. So, substituting the values, we get the value of VR2 square as 61.9 meter square per second square. So, substituting the value of VR2 square here, we get the value of kinetic energy at output as 30.95 meter square per second square, and the power input at the inlet per unit mass is given as G into the net head available, which is 2285.73 meter square per second square. So, the ratio comes out as the percentage ratio comes out as 1.35%. So, all the parts of this problem has been discussed. So, by this I end the lecture on Pelton wheel or Pelton turbine. In the next lecture, we will start with the Francis turbine problems.